Hello there. Welcome to Ancient Earth Documentary Podcast. In this episode, we focus on why dinosaurs lived longer than any other large animals. Dinosaurs ruled this planet for 165 million years. Modern humans have been around for roughly 300,000. We haven't even made it to 500,000 yet, and we're already wondering if we'll see the next century. Meanwhile, these ancient reptiles dominated Earth through climate shifts, asteroid impacts that weren't the final one, volcanic eruptions that blotted out the sun, and continental drift that completely rearranged the map. They didn't just survive. They thrived, diversified, and spread to every corner of the globe. No other group of large land animals has ever come close to that kind of tenure. You'd think creatures that ruled for that long must have lived forever as individuals, right? That a Tyrannosaurus rex might have celebrated its 100th birthday, or that the massive sauropods with necks stretching toward the sky could have lived for centuries like some ancient tortoise. For decades, scientists believed exactly that. Early paleontologists looked at the sheer size of these animals and assumed they aged like modern reptiles, slowly and steadily, potentially living for hundreds of years. Turns out, they were completely wrong. When researchers finally developed the tools to accurately measure dinosaur lifespans by examining growth rings in fossil bones, much like counting tree rings, they discovered something shocking. Most dinosaurs died young. A Tyrannosaurus rex that reached 30 years old was ancient by its species standards. The giant sauropods that weighed as much as 10 elephants rarely made it past 50 or 60. These weren't creatures that lived for centuries. They burned bright and fast, growing at rates that seem almost impossible, reaching enormous sizes in just a couple of decades, then dying while still technically growing. This creates a fascinating paradox. As a group, dinosaurs achieved the longest dominance of any large land animals in history. But as individuals, many lived shorter lives than modern elephants or whales. How does that work? What allowed them to succeed for so long when their individual lifespans were surprisingly brief? The answer involves metabolism, reproduction, evolution, and a respiratory system so efficient it puts modern mammals to shame. Let's start with what we mean by dominance. When we say dinosaurs ruled for 165 million years, we're talking about their time as the dominant terrestrial vertebrates on Earth. They first appeared around 245 million years ago during the Middle Triassic period. But they weren't in charge yet. Early dinosaurs were relatively small, and they shared the landscape with other reptiles that were often larger and more successful. But then came the Triassic-Jurassic extinction event about 201 million years ago. Massive volcanic eruptions released enormous amounts of carbon dioxide and sulfur dioxide into the atmosphere. Temperatures swung wildly, ocean chemistry changed, and when the dust settled, roughly 70 to 75% of all species were gone. The dinosaurs survived. More importantly, they inherited the Earth. With their competition largely eliminated, dinosaurs rapidly diversified and spread. They evolved into countless forms, from chicken-sized predators to multi-ton herbivores with bodies that defied physics. They developed armor, horns, elaborate crests, and weaponized tails. Some learned to hunt in packs. Others became solitary titans that nothing dared approach. Throughout the Jurassic and Cretaceous periods, dinosaurs were the undisputed rulers of the land. Mammals existed during this entire time, but they were small, mostly nocturnal, and spent 100 million years living in the shadows, literally and figuratively, rarely growing larger than a house cat. This is critical to understand. For over 100 million years, mammals were prey. They were snacks. They lived short, fearful lives, reproducing quickly because their odds of reaching old age were essentially zero. This period was so long and so dominant for dinosaurs that it fundamentally shaped mammalian evolution in ways we're still dealing with today. More on that later because it explains something surprising about why modern mammals, including us, age the way we do. During their reign, dinosaurs weren't just surviving, they were innovating. Different lineages independently evolved similar solutions to similar problems. Take air sacs, for example. Modern birds have complex respiratory systems with air sacs that extend from their lungs into their bones, making them lighter and allowing them to breathe more efficiently. Dinosaurs had the same system. In fact, evidence suggests this trait evolved independently at least 3 times in different dinosaur groups: in pterosaurs, in theropods, which includes Tyrannosaurus rex and eventually birds, and in sauropodomorphs, the long-necked giants. Why does this matter? Because the Mesozoic era, the age of dinosaurs, had significantly less oxygen in the atmosphere than today. Estimates suggest oxygen levels were only 10 to 15%, compared to 21% now. That's thin air. It's the equivalent of living at high altitude. Yet dinosaurs not only survived, they became massive. Their super-efficient respiratory systems allowed them to sustain activity levels that would have been impossible for similarly sized animals with mammalian lungs. This gave them an enormous advantage. They could grow larger, move faster, and dominate ecosystems in ways that other animals simply couldn't match. Dinosaurs also benefited from favorable environmental conditions for much of their reign. The climate during the Jurassic and Cretaceous periods was generally warmer and more humid than today. There were no polar ice caps. Forests grew in Antarctica. Sea levels were higher, creating shallow inland seas that moderated temperatures and increased coastal habitats. Plant life was abundant, providing endless food for herbivores, which in turn fed the carnivores. This wasn't a paradise. Extreme droughts, floods, and volcanic activity still occurred. But overall, the conditions supported large body sizes and high biodiversity. Their success wasn't just about favorable conditions, though. Dinosaurs were adaptable. When climates shifted, they evolved. When continents drifted apart, they spread to new landmasses. Fossils have been found on every continent, including Antarctica. They occupied nearly every ecological niche available to large land animals. There were dinosaur herbivores, carnivores, omnivores, and specialists that fed on specific types of plants or prey. Some lived in forests, others in open plains, and some in coastal or swampy environments. This diversity meant that even when one group struggled, others thrived. So dinosaurs as a lineage were remarkably successful. But what about individual dinosaurs? How long did they actually live? For a long time, nobody really knew. Early paleontologists made educated guesses based on modern reptiles. Crocodiles and large tortoises can live for many decades, some for over a century. Scientists assumed dinosaurs, being reptiles, followed similar patterns. The largest sauropods were estimated to live for 200 or 300 years. It seemed logical. After all, they were enormous, and in nature, larger animals generally live longer. Elephants live longer than mice. Whales outlive dolphins. Why wouldn't a creature weighing 80 tons live for centuries? The problem was, nobody had a reliable way to test this assumption until relatively recently. The breakthrough came from bone histology, the study of bone microstructure. When paleontologists began cutting thin sections of fossilized dinosaur bones and examining them under microscopes, they discovered something remarkable. The bones contained growth rings, similar to tree rings. Each ring represented a year of growth. By counting the rings, scientists could determine how old a dinosaur was when it died. The results shocked everyone. Tyrannosaurus rex, one of the largest and most fearsome predators ever to walk the earth, had a maximum lifespan of around 30 years. Most didn't even make it that far. The famous specimen known as Sue, one of the most complete T-Rex fossils ever found, was 28 years old at death. That was considered elderly for the species. These animals didn't grow slowly and steadily for decades like crocodiles. They exploded in size. A juvenile T-Rex might weigh around 50 kilograms. 15 to 18 years later, it could weigh 5,000 to 8,000 kilograms. That's a growth rate of several hundred kilograms per year during peak adolescence. It's staggering. The giant sauropods showed similar patterns. Apatosaurus, a long-necked herbivore that could weigh 25,000 kilograms, reached adult size in approximately 15 years. Its maximum growth rate exceeded 5,000 kilograms per year. Think about that for a moment. This animal was packing on the weight of a small car every single year during its teenage growth spurt. Even larger sauropods like Alamosaurus, which could exceed 32,000 kilograms, reached full size within 45 years. Current estimates suggest the largest sauropods lived for 60 to 80 years at most, comparable to modern elephants, despite being 10 times heavier. This was a complete reversal of earlier assumptions. Dinosaurs weren't slow-growing reptiles that lived for centuries. They were fast-growing animals that lived relatively brief lives. But here's the question. If they didn't live that long individually, how did they dominate for so long collectively? Part of the answer lies in reproduction. Dinosaurs laid eggs, often in large clutches. A single female could produce dozens of offspring in a breeding season. This is very different from mammals like elephants or whales, which have long gestation periods and typically produce only one offspring at a time. Elephants take nearly 2 years to give birth and then invest years raising their calves. Whales are similar. This slow reproduction means natural selection favors longer lifespans in these species. You need time to raise multiple generations of offspring to pass on your genes. Dinosaurs didn't have that constraint. They could produce many offspring quickly, and those offspring grew rapidly. Natural selection didn't need to favor extreme longevity because a dinosaur could successfully reproduce and pass on its genes within a relatively short time frame. This is speculative, but it's supported by what we see in modern animals. Species that reproduce quickly and in large numbers generally don't live as long as species that invest heavily in a few offspring. Dinosaurs followed the former strategy, which allowed rapid population turnover and faster evolutionary adaptation. This brings us to another crucial factor in their long dominance, their metabolism. For decades, scientists debated whether dinosaurs were cold-blooded like modern reptiles or warm-blooded like mammals and birds. The truth appears to be somewhere in between, a state called mesothermy. Different dinosaur groups had different metabolic rates, but most fell between modern reptiles and modern mammals. Some, particularly the theropods, the group that includes T-Rex and eventually evolved into birds, had metabolic rates comparable to, or even higher than modern birds. That's remarkable because bird metabolism is extremely high, higher than most mammals. What does this mean practically? It means dinosaurs could sustain activity levels that cold-blooded reptiles couldn't match. A crocodile needs to bask in the sun for hours to warm up enough to hunt. A dinosaur with a higher metabolic rate could be active throughout the day and night, regardless of external temperatures. This gave them a competitive edge. But higher metabolism comes with trade-offs. It requires more food, generates more internal heat, and burns through resources faster. This likely contributed to their relatively shorter lifespans compared to what we'd expect from such large animals. They lived fast in a metabolic sense. Their unique respiratory system played into this as well. Those bird-like air sacs didn't just help with oxygen intake in a low-oxygen world. They also provided efficient cooling. When you're a multi-ton animal generating enormous amounts of metabolic heat, getting rid of that heat is a serious challenge. Mammals sweat or pant. Dinosaurs had a built-in radiator system that circulated air through their bones and body cavity, cooling them from the inside out. This allowed them to maintain high activity levels without overheating, another advantage that contributed to their evolutionary success. Now, let's connect these pieces. Dinosaurs dominated for 165 million years, not because individuals lived for centuries, but because they were extraordinarily well adapted to their environment. They had efficient respiratory systems that worked in low oxygen conditions. They had metabolisms that allowed sustained activity. They reproduced quickly and in large numbers. They grew rapidly, reaching adult size and reproductive maturity in a fraction of the time it takes modern, large mammals. And they were diverse, occupying every available niche and adapting quickly when conditions changed. This combination of factors created a positive feedback loop. Fast growth meant rapid generational turnover. Rapid turnover meant faster evolution. Faster evolution meant better adaptation to changing environments. Better adaptation meant continued dominance. Individual dinosaurs didn't need to live for centuries because the species as a whole were constantly refreshing, adapting, and improving. But there's another layer to this story, one that involves what happened to the mammals living in the dinosaurs' shadow. While dinosaurs were thriving and evolving into countless forms, mammals were stuck. They stayed small. They stayed nocturnal. They lived short, high-stress lives as prey animals. For over 100 million years, this was the mammalian existence, and it had profound consequences. Scientists now call this the longevity bottleneck hypothesis, and it explains something fundamental about why mammals, even large ones, age differently than reptiles. The longevity bottleneck hypothesis suggests that mammals carry genetic scars from the age of dinosaurs. During those 100 million years of living in the shadows, mammals evolved to prioritize one thing above all else: reproducing quickly before something ate them. When you're a small, furry creature in a world of giant predators, investing biological resources into long-term cellular maintenance makes no evolutionary sense. You might not survive long enough for those investments to pay off. Better to reproduce early and often, even if it means your body wears out faster. This shaped mammalian biology at a fundamental level. Genes and pathways associated with longevity, things like enhanced DNA repair mechanisms, superior cellular regeneration, and negligible senescence, these were either lost or downregulated because they provided no survival advantage. A mouse that could theoretically live for 50 years but didn't reproduce until age 10 would be evolutionarily outcompeted by a mouse that bred at 6 months and died at 3 years. The pressure was relentless, and it lasted for geological timescales. 100 million years is enough time for evolution to completely reshape an organism's fundamental biology. And that's exactly what happened to mammals. Here's where it gets interesting. Reptiles and amphibians that weren't under the same evolutionary pressure retained these longevity mechanisms. Some modern reptiles exhibit what scientists call negligible senescence, meaning they don't show typical signs of aging. Their mortality risk doesn't increase with age the way it does in mammals. An 80-year-old crocodile is just as likely to survive the next year as a 20-year-old crocodile, assuming neither gets killed by external factors. Mammals don't work this way. Even long-lived mammals like elephants and whales show clear aging phenotypes. Their cells accumulate damage over time. Their tissues degrade. Their risk of death increases with age. They've evolved longer lifespans than their ancestors, yes, but they did so within constraints. The genetic toolkit for extreme longevity was already gone, lost during the age of dinosaurs. Consider the tuatara, a reptile from New Zealand that looks like a lizard but belongs to its own ancient order. Tuataras can live over 100 years and age remarkably slowly. A 2022 DNA analysis revealed they've retained anti-aging genes that mammals simply don't have anymore. These aren't new evolutionary innovations. They're ancient mechanisms that mammals lost. Why does this matter for understanding dinosaurs? Because it highlights just how different the selective pressures were for animals living in the Mesozoic versus animals living today. Dinosaurs weren't operating under the same constraints as modern mammals. They had different metabolisms, different growth strategies, and different evolutionary trade-offs. But there's a paradox here that's worth examining. If dinosaurs had these advantageous traits, efficient respiratory systems, mesothermic metabolism, rapid growth rates, why didn't they live longer as individuals? Why did a 40-ton Apatosaurus only live 70 to 80 years, when modern elephants, at a fraction of the size, can reach similar ages? The answer involves understanding how different organisms allocate their biological resources. life history theory in biology describes a fundamental trade-off between growth, reproduction, and maintenance. You have finite energy and resources. Invest heavily in rapid growth and lots of offspring, and you have less to invest in long-term cellular maintenance. Invest in maintenance and longevity, and you grow slower and reproduce less frequently. Dinosaurs chose the growth and reproduction strategy, and it worked spectacularly well for them. Apatosaurus could reach 25,000 kilograms in just 15 years. That's a maximum growth rate of over 5,000 kilograms per year. Think about that number, 5,000 kilograms in 1 year. That's adding the weight of a full-grown elephant annually during peak growth. Compare that to modern elephants, which take 20 to 25 years to reach full size at about 5 to 6 tons. Elephants grow much slower, reproduce less frequently, one calf every 4 to 5 years, and invest more in longevity. They reach sexual maturity later and have fewer offspring over their lifetime. But each offspring gets more parental investment, and the parents themselves live longer to potentially have more breeding opportunities. These are fundamentally different strategies, shaped by fundamentally different environments. The Mesozoic world, with its lower oxygen levels, different climate patterns, and unique ecological dynamics, favored the dinosaur approach. Rapid growth meant reaching a size where you were safe from most predators sooner. Large clutches of eggs meant more offspring survived despite high juvenile mortality. Shorter lifespans were acceptable because generational turnover drove adaptation. The modern world favors the mammalian approach for large terrestrial animals. Slower growth, fewer offspring, longer parental care, extended lifespans. Neither strategy is inherently superior. They're optimized for different conditions. But here's something that often gets overlooked in these comparisons. When we talk about dinosaur lifespans, we're usually discussing how long they could potentially live, their maximum lifespan. That's different from life expectancy, which is how long they actually lived on average. For dinosaurs, these numbers were probably very different. Evidence from bone histology suggests many dinosaurs died while still growing, before reaching their theoretical maximum size. A 30-year-old T-Rex wasn't common. Most died younger, probably much younger. Predation, disease, injury, starvation, environmental catastrophes, these took their toll. Just because an animal can live 30 years doesn't mean most individuals do. This is true for modern animals too. African elephants can live 70 years, but average life expectancy in the wild is much lower, probably around 40 to 50 years. Most elephants don't die of old age. They die from drought, disease, poaching, or conflicts with other elephants. For dinosaurs, the gap between potential lifespan and actual life expectancy was probably even larger. They lived in a more dangerous world. No modern large predator faces the same level of competition and environmental challenges that Mesozoic dinosaurs did. Injuries that modern mammals might survive were death sentences in an era before antibiotics or modern immune systems. So when we say T, Rex lived about 30 years. We mean that's approximately when their growth stopped and when they would have started showing signs of senescence if they survived that long. Most didn't. Most T-Rexes probably died in their teens or early 20s, killed by rivals, injured while hunting, or starved during lean times. This brings us back to the question of how dinosaurs managed to dominate for so long, despite relatively short individual lifespans. The answer lies in understanding evolution as a species-level phenomenon, rather than an individual one. Natural selection doesn't care about individual longevity, it cares about reproductive success. A species that reproduces quickly and adapts rapidly will outcompete a species that reproduces slowly, even if individuals of the slower species live longer. Dinosaurs excelled at rapid adaptation. Their fast growth rates meant short generation times. Short generation times meant evolution could work faster. When environmental conditions changed, and they changed frequently during the Mesozoic, dinosaur populations could adapt within a few thousand years. That's nothing in geological time. Mammals under dinosaur rule couldn't compete on these terms. They were locked into their small-bodied, quick-breeding niche. Any mutation that made them larger or slower to reproduce would have been selected against because it would have made them more visible to predators without providing compensating advantages. The dinosaurs had already claimed all the large-bodied niches. There was nowhere for mammals to go evolutionarily. This created a stable but stagnant situation for mammals. They diversified within their constraints, developing different teeth for different diets, different locomotion styles, even early forms of powered flight in some lineages. But they stayed small. For over 100 million years, the largest mammals were about the size of a modern badger. Most were much smaller. Then 65 million years ago, everything changed. An asteroid roughly 10 kilometers in diameter slammed into what's now the Yucatan Peninsula with the force of billions of nuclear weapons. The impact itself killed everything within hundreds of kilometers instantly. The resulting shockwave, wildfires, and tsunamis killed millions more in the following hours and days. But the real devastation came from what happened next. Debris thrown into the atmosphere blocked out the sun for months, possibly years. Photosynthesis stopped. Plants died. Herbivores starved. Carnivores that depended on those herbivores starved. The entire food chain collapsed from the bottom up. Large animals were hit hardest. They needed more food, more territory, more resources. When those resources disappeared, they died. Small animals, the ones that could shelter in burrows, that could survive on seeds and insects and detritus, they had a chance. Not a good chance, but a chance. The dinosaurs didn't make it. About 75% of all species on Earth died in the months and years following the impact. But here's what matters for our story. The survivors weren't random. They followed a pattern. Small body size helped. The ability to eat diverse foods helped. Living in burrows or water helped. Being able to go dormant or survive on minimal resources helped. Mammals had spent 100 million years perfecting exactly these survival strategies. Not by choice, by necessity. Every trait that helped them survive under dinosaur rule suddenly became the key to surviving the apocalypse. In the immediate aftermath, the world belonged to nothing and no one. It was a wasteland. But slowly, very slowly, life returned. Plants grew back from seeds and spores. Insects emerged from underground refuges. And the survivors began to explore a world that suddenly had room. So much room. For the first time in over 100 million years, there were no dinosaurs. No massive predators patrolling the forests. No herds of giant herbivores stripping the vegetation. No territorial disputes between animals the size of buildings. The ecological niches that dinosaurs had occupied were empty, and evolution abhors a vacuum. This is where mammals finally got their chance. Within a few million years, a blink of an eye geologically, mammals began diversifying at an explosive rate. They grew larger. They developed new body plans. They spread into environments dinosaurs had dominated. They evolved specialized teeth, specialized limbs, specialized senses. The constraints were gone. The genetic potential that had been suppressed for so long could finally express itself. But here's the crucial point. The longevity bottleneck remained. Those 100 million years under dinosaur rule had fundamentally altered mammalian biology. The genes and cellular mechanisms for extreme longevity, the kind we see in some reptiles and fish, had been lost or deactivated. Mammals had evolved around a strategy of living fast and reproducing quickly. That strategy was so deeply embedded in their biology that it couldn't simply be reversed once dinosaurs were gone. Even as mammals grew larger and conquered new ecological niches, they carried this genetic legacy with them. This is the longevity bottleneck hypothesis. It suggests that the relatively short lifespans of modern mammals, compared to some reptiles, are a direct consequence of evolutionary pressures during the age of dinosaurs. For those 100 million years, there was no selective advantage to living a long time. In fact, there were disadvantages. Longer-lived animals typically reproduce more slowly. They invest more energy in maintaining their bodies. they take longer to reach sexual maturity. In a world where being small, hidden, and quick to reproduce was the only path to survival, these traits were liabilities. Consider what this means. A modern elephant lives about 70 years in the wild. Impressive by mammalian standards. But an Aldabra giant tortoise can live 150 years, sometimes longer. Jonathan, a Seychelles giant tortoise currently living on St. Helena, is approximately 191 years old. He hatched before the telephone was invented. These aren't even the most extreme examples. Bowhead whales can live over 200 years. Some fish and invertebrates show negligible senescence, meaning they don't seem to age in any meaningful way at all. Why can't mammals do this? The answer lies in cellular maintenance systems. Long-lived animals tend to have superior DNA repair mechanisms, more effective antioxidant systems, and better ways of dealing with cellular damage. These mechanisms require specific genes and metabolic pathways. Mammals appear to have lost or downregulated many of these during the Mesozoic. When you're a shrew-sized creature expecting to die within a year or two anyway, investing energy in long-term cellular maintenance is wasteful. Better to put those resources into reproduction. Make more offspring, make them quickly, hope some survive. This evolutionary logic held true for so long that it became baked into mammalian biology. Even after mammals grew large and dominant, even after they evolved into elephants and whales and humans, they couldn't simply reactivate genes that had been silent for millions of generations. Evolution doesn't work backwards that easily. You can't just flip a switch and restore lost capabilities. Once a genetic pathway is lost, regaining it requires building it from scratch through random mutation and selection. That takes time, enormous amounts of time. So modern mammals age. We show clear senescence. Our bodies accumulate damage over time. Our cells become less efficient at repair. Our organs slowly fail. This isn't inevitable for all animals. It's specifically a mammalian characteristic, likely inherited from our dinosaur-era ancestors. The tuatara, a reptile from New Zealand, shows remarkably slow aging and can live well over 100 years. Recent DNA analysis suggests it has retained genetic pathways for longevity that mammals lost. It never went through the bottleneck. But wait. If this hypothesis is correct, we should see evidence of it in the fossil record and in modern biology. And we do. Mammals are conspicuously absent from the list of animals that show negligible senescence or extreme longevity relative to their body size. Every mammal shows aging. Every mammal has a finite lifespan that correlates roughly with its size and metabolism. There are no mammalian equivalents of the 200-year-old bowhead whale when you adjust for size differences. Even the largest mammals, blue whales, live less than 100 years typically. Large sharks of comparable size can live twice that long. The evidence goes deeper. At the cellular level, mammalian cells show characteristics consistent with being optimized for rapid turnover rather than long-term stability. Our telomeres, the protective caps on our chromosomes, shorten with each cell division. This limits how many times our cells can divide before dying. Some reptiles and fish have telomerase activity in their adult cells, allowing them to maintain or even rebuild their telomeres. Most adult mammals don't. Our telomerase is mostly shut off after development. Another legacy of the bottleneck. Even our regenerative capabilities seem limited compared to some other vertebrates. Salamanders can regrow entire limbs. Some fish can regenerate heart tissue. Mammals can't do either. We heal wounds through scarring, a faster but less perfect solution. Our regenerative abilities are tuned for short-term survival, not long-term maintenance. Again, this makes sense if your ancestors spent 100 million years not expecting to live long enough for perfect healing to matter. The implications of this are profound. It means that human aging, and the aging of all mammals, isn't just a fact of life. It's a specific evolutionary outcome shaped by a specific historical circumstance. If dinosaurs had never existed, or if they'd gone extinct earlier, or if mammals had somehow avoided being suppressed for so long, we might age completely differently. We might live for centuries. We might not age at all in the traditional sense. The way we experience time, the way we structure our societies, the way we think about life and death, all of it might be fundamentally different. This also means that overcoming aging in humans isn't impossible, but it's fighting against deep evolutionary programming. We're not just dealing with a few genes that need tweaking. We're dealing with entire metabolic and cellular systems that were optimized for a different survival strategy millions of years ago. Extending human lifespans significantly will require understanding and potentially rebuilding these fundamental systems. Not impossible, but far more complex than early anti-aging researchers imagined. But let's return to dinosaurs for a moment, because there's an interesting counterpoint here. If short lifespans were such a disadvantage, how did dinosaurs dominate for so long despite living relatively short lives themselves? Remember, even the largest sauropods probably only lived 70 or 80 years. T-Rex lived about 30. These aren't exceptional lifespans for their sizes. An elephant-sized dinosaur lived about as long as an actual elephant, sometimes less. So why did this work for dinosaurs, but create a bottleneck for mammals? The answer is about ecological position. Dinosaurs could afford relatively short lifespans because they were the dominant animals. They faced fewer predators. They had access to abundant resources. Their survival rates, while not perfect, were high enough that their reproductive strategy worked. Mammals under dinosaur rule couldn't afford the same strategy. They were prey. They were competing for scraps. Their survival rates were much lower, so they needed even faster reproduction, even shorter generation times, even less investment in longevity. The pressure on mammals was much more intense than the pressure on dinosaurs. This creates a fascinating asymmetry. Both groups had relatively short lifespans, but for different reasons and with different consequences. Dinosaurs lived fast because they could afford to. Mammals lived fast because they had no choice. When the asteroid hit, this difference became crucial. Dinosaurs had optimized for a world of abundance and dominance. Mammals had optimized for a world of scarcity and danger. The post-impact world was definitely the latter. So in a sense, the longevity bottleneck wasn't just about lifespan. It was about adaptability. Mammals had evolved to be generalists, to survive in marginal conditions, to make do with whatever was available. These traits, forged during their long subordination, became their salvation. But they came at a cost. The cost was longevity. The cost was the cellular machinery for indefinite life. The cost was the genetic potential to be like a tortoise or a bowhead whale, barely aging across centuries. Human beings today carry this legacy in every cell. We age because our distant ancestors couldn't afford not to. We die because they needed to reproduce quickly and couldn't waste resources on long-term survival. The wrinkles on your face, the grey in your hair, the gradual decline of your body, all of it traces back to small, furry creatures hiding from dinosaurs in the darkness of the Mesozoic. That's the true long-term impact of the dinosaur age. Not just that they existed, not just that they dominated, but that they fundamentally shaped the biology of the animals that came after them. And mammals weren't the only ones affected. Birds, the direct descendants of theropod dinosaurs, show similar aging patterns to mammals despite their different evolutionary path. They too have relatively short lifespans for their sizes, likely for similar reasons. Flying requires high metabolism. High metabolism means rapid aging. The constraints are different, but the outcome is similar. Even the survivors of the dinosaur lineage carry limitations imposed by their history. This brings us to a larger question about evolution and contingency. How much of what we are is actually chosen, and how much is just inherited constraint? Evolution doesn't work like an engineer with a blank slate. It works like a renovator with a fixed budget, limited materials, and a building that can't be shut down during construction. Every change has to happen while the system keeps running. Every adaptation has to work with what's already there. You can't just tear down the foundation and start over. This is why evolutionary history matters so profoundly. It's not just about understanding the past. It's about understanding why the present looks the way it does, why certain solutions exist and others don't, why some problems get solved and others persist across millions of years. The longevity bottleneck is a perfect example of this principle in action. Mammals didn't choose short lifespans. They inherited a biological architecture that made long lifespans prohibitively expensive. Consider what it would take to reverse the bottleneck. You'd need to restore or rebuild all the cellular machinery that was lost or degraded during those 100 million years under dinosaur rule. DNA repair mechanisms that were simplified, regenerative pathways that were shut down, tumor suppression systems that were scaled back, cellular quality control processes that were deemed too costly. All of these systems interact with each other in complex ways. You can't just flip a switch and turn longevity back on. Each change would require coordinating modifications across hundreds or thousands of genes. Each modification would need to be tested by natural selection, and it would all have to happen without breaking anything currently essential. The metabolic constraints make it even harder. Mammals are warm-blooded. We maintain constant high body temperatures. This requires burning enormous amounts of energy compared to reptiles. That energy has to come from somewhere, and it creates its own problems. High metabolism means more cellular activity. More cellular activity means more opportunities for errors. More errors mean more need for repair mechanisms. More repair mechanisms mean more energy expenditure. It's a vicious cycle. You can invest in longevity, but only up to a point before the costs become unsustainable. Reptiles don't face this same trade-off, at least not as severely. A tortoise can afford to invest heavily in cellular maintenance because its baseline energy costs are so much lower. It doesn't need to keep warm. It doesn't need to move as much. It can sit still for days or weeks without eating. This gives it metabolic room to allocate resources toward long-term survival rather than immediate reproduction. Mammals can't do this. We need constant fuel. We need to stay active. We need to reproduce before we run out of time. This creates a fundamental asymmetry in how different animal groups age. It's not that reptiles have discovered some secret to immortality. It's that they're playing a different game with different rules. Their low metabolism allows strategies that simply aren't available to mammals. And mammals, locked into their high-energy lifestyle by evolutionary history, can't easily switch strategies, even if it would be advantageous. But here's where it gets really interesting. Some mammals have managed to push back against these constraints. Bowhead whales live over 200 years. Humans can reach well past a century. Naked mole rats show almost no signs of aging throughout their 30-year lifespans. These species prove that the bottleneck isn't absolute. It's possible to evolve longer life within the mammalian framework. The question is how they did it and why it's so rare. The answer seems to involve size, ecology, and specific genetic modifications. Bowhead whales are enormous. Their size alone protects them from most predators and allows them to store vast energy reserves. They live in cold Arctic waters where their blubber provides insulation, reducing the metabolic cost of maintaining body temperature. And they've evolved specific genetic changes that enhance DNA repair and suppress cancer more effectively than other mammals. Size bought them time. Ecology bought them efficiency. Genetics bought them maintenance. Together, these factors pushed back the aging clock. Humans took a different route. We're not particularly large compared to many mammals. Our ecology doesn't obviously favor longevity. What we have instead is something unique: culture. We can pass information across generations without genetic inheritance. We can modify our environment to reduce threats. We can care for sick and elderly individuals who would die in nature. This cultural buffering changes the evolutionary equation. Suddenly, there's value in living long enough to accumulate knowledge, to teach, to contribute to group survival beyond your reproductive years. Natural selection starts favoring traits that extend lifespan, even at the cost of early reproduction. But even humans can't escape the bottleneck entirely. We age, we get cancer, we accumulate cellular damage, we die. Our maximum lifespan, around 120 years, is impressive for a mammal, but pathetic compared to tortoises or bowhead whales. We've pushed the boundaries, but we haven't broken through them. The constraints forged in the Mesozoic still bind us. Naked mole rats are perhaps the most fascinating case. These bizarre rodents live in underground colonies in East Africa. They're about the size of mice, but live 10 times longer. They barely show signs of aging. They almost never get cancer. Their cells maintain function far longer than those of other rodents. How? The answer involves multiple adaptations. They have enhanced protein quality control. They're better at fixing misfolded proteins before they cause problems. They have improved DNA repair. They have different metabolic chemistry that produces less cellular damage. They tolerate low oxygen and high carbon dioxide, conditions that would kill most mammals. And critically, they live in stable underground environments with minimal predation, which removes much of the pressure for rapid reproduction. What all these cases show is that escaping the longevity bottleneck requires multiple factors aligning. You need either large size or protected ecology or both. You need specific genetic changes that enhance maintenance without breaking metabolism. You need an evolutionary context where longer life provides real advantages that outweigh the costs. These conditions are rare. Most mammals don't meet them. So most mammals age and die on schedules that would seem absurdly short to a tortoise or a whale. This brings us back to the question of contingency. If the asteroid hadn't hit, if dinosaurs had continued to dominate, would mammals have ever evolved long lifespans? Probably not. The ecological pressure would have remained. Small size would have remained advantageous. Rapid reproduction would have remained necessary. The bottleneck would have persisted indefinitely. In that alternate timeline, mammals might still be rat-sized creatures, living fast and dying young, while dinosaurs continued their 100-million-year reign. But the asteroid did hit. The dinosaurs, except for birds, died out. Mammals inherited an empty world full of opportunities. Within 10 million years, they'd radiated into every ecological niche the dinosaurs had occupied. Within 30 million years, they'd produced giants that rivaled sauropods in size. And within 65 million years, they'd produced a species capable of understanding its own evolutionary history and asking questions about why it ages. Yet even with all this success, with all this diversification, with all this evolutionary time, mammals still carry the scars of their bottleneck period. We've adapted, we've specialized, we've conquered nearly every habitat on Earth. But we haven't fundamentally escaped the constraints imposed by our deep past. Our cellular biology still reflects decisions made by natural selection in a world we never experienced, shaped by pressures we never faced, solving problems we no longer have. This is the strange reality of evolutionary inheritance. You are not just the product of your own lifetime, or even your species' history. You're the product of every generation, stretching back to the first living cell. Every ancestor that survived left marks on your biology. Every crisis they endured shaped the tools you inherited. Every compromise they made set boundaries on what you can become. Evolution is not just about adaptation to current conditions. It's about carrying forward the accumulated baggage of billions of years, for better and worse. The longevity bottleneck is just one example of this principle. There are others. Mammals have 7 neck vertebrae. Almost all of us, from giraffes to humans to whales. Why 7? probably because of developmental constraints inherited from early mammal ancestors. Changing that number proves difficult without breaking other systems. So we're stuck with 7. Our eyes have blind spots where the optic nerve passes through the retina. Poor design from an engineering perspective, but inherited from our fish ancestors and now too integrated to easily fix. We get hiccups because we inherited our breathing apparatus from amphibians who needed to switch between air and water. We get back pain because we evolved from quadrupeds and our spines aren't perfectly optimized for upright walking. Every species carries similar baggage. Every lineage has its own bottlenecks, its own constraints, its own inherited limitations. Evolution is brilliant at optimization within constraints, but remarkably poor at starting over from scratch. Once a solution gets locked in, once developmental pathways get established, once genetic networks get interconnected, change becomes progressively harder. You end up with systems that work well enough to survive, but that no intelligent designer would ever create intentionally. This is why studying evolutionary history matters. It reveals the difference between what is and what could be. It shows you the constraints that aren't obvious from just looking at modern organisms. It explains why certain changes happen easily and others never happen at all. And it gives you perspective on the deep contingency of life, how profoundly the past shapes the present in ways that persist across incomprehensible timescales. So when you look at human aging, when you see the grey hair and the wrinkles and the gradual decline, remember, this isn't just biology, it's history. It's the legacy of small mammals hiding from dinosaurs 100 million years ago. It's the echo of an asteroid impact 65 million years ago. It's the accumulated weight of every generation between then and now, each one surviving just long enough to pass forward their genes and their constraints. You are not just alive. You are the temporary custodian of an ancient inheritance, shaped by crises you never knew existed. And that inheritance goes deeper than you might think. Because those dinosaurs, the ones that kept our ancestors small and desperate, weren't just ecological competitors. They were architects of mammalian biology in ways that still constrain us today. Consider this. Dinosaurs ruled Earth for approximately 165 million years. That's not a typo. 165 million years of dominance. For context, modern humans have existed for maybe 300,000 years. All of recorded human history spans roughly 5,000 years. The entire age of mammals, the time since dinosaurs went extinct, is only 65 million years. Dinosaurs had more than twice that long at the top. During their reign, they didn't just occupy ecological niches, they monopolized them. They filled every available role for large terrestrial animals. Herbivores, carnivores, omnivores, all dinosaurs. Mammals existed throughout this period, but they were relegated to the margins. Small, nocturnal, hiding. For over 100 million years, being a mammal meant being prey, not predator. It meant living fast and dying young, because anything else was a luxury you couldn't afford. That timescale matters. 100 million years is enough for evolution to strip away traits that aren't immediately useful. It's enough to lose entire genetic pathways. It's enough to fundamentally rewire how your biology operates at the cellular level. And here's where it gets interesting. Dinosaurs themselves, they didn't live particularly long lives. Not as long as you'd expect anyway. For decades, scientists assumed that the largest dinosaurs must have lived for centuries. Something the size of a Patasaurus, weighing 25,000 kilograms, stretching over 20 meters long, surely that animal lived for 200 or 300 years. The logic seemed sound. Large animals today tend to live longer. Elephants reach 70 years. Bowhead whales can hit 200. A creature 10 times the mass of an elephant should live even longer. Right? Wrong. Bone analysis tells a different story. Scientists can determine dinosaur age the same way you'd age a tree. Growth rings. Bone tissue lays down annual markers, visible under microscopy, that record each year of growth. When paleontologists started examining dinosaur bones this way in recent decades, they found something unexpected. Most dinosaurs died young, really young. Tyrannosaurus rex, the apex predator of the Cretaceous, lived approximately 30 years maximum. Most individuals died in their 20s. They reached full size around age 25 and didn't survive much beyond that. Even more surprising, T-Rex grew explosively fast. A juvenile could gain over 600 kilograms per year during peak growth. It took only 15 to 18 years to reach adult proportions, transforming from a hatchling into an 8-ton killing machine in less than 2 decades. The giant sauropods? Apatosaurus reached its 25,000 kilogram adult mass in about 15 years. That's a growth rate exceeding 5,000 kilograms per year at peak. Diplodocus, similarly massive, lived maybe 70 or 80 years tops. About the same as a modern elephant, despite being vastly larger. These ages shocked researchers. The assumption had always been that size equals longevity, but dinosaurs broke that rule completely. Why? The answer lies in their metabolism. Dinosaurs weren't cold-blooded like modern reptiles, but they weren't warm-blooded like mammals either. They occupied a middle ground, what scientists call mesothermy. Their metabolic rates were higher than reptiles but lower than most mammals. Some lineages, particularly the theropods and sauropods, ran even hotter. Recent research suggests certain dinosaurs had metabolic rates comparable to modern birds, which are actually higher than mammals. This metabolic intensity enabled their rapid growth. It let them reach enormous sizes quickly, but it came with a cost. High metabolism burns through resources faster. It accumulates cellular damage more rapidly. It shortens lifespan. Compare this to modern reptiles. Crocodiles grow slowly and live long. Deinosuchus, a giant crocodile contemporary with dinosaurs, took nearly 50 years just to reach full size. It achieved similar length to T-Rex, but needed 3 times as long to get there. That slow growth meant a slower metabolism, less oxidative stress, potentially longer total lifespan. Dinosaurs traded longevity for speed. They grew fast, reproduced early, died relatively young. This strategy worked brilliantly for 165 million years, because the world they lived in rewarded it. Resources were abundant. Climate was favorable. Competition was primarily with other fast-growing dinosaurs, but for mammals living in that same world, speed was mandatory, not optional. When you're small and constantly hunted, when every night might be your last, when predators are everywhere and resources are scarce, you can't afford to grow slowly. You can't afford to delay reproduction until middle age. You can't afford to invest in longevity systems that might pay off decades down the line. You need to mature fast, reproduce fast, and hope some of your offspring survive. Natural selection doesn't care about your potential lifespan in a safe environment. It cares about reproductive success in the actual environment you inhabit. And for 100 million years, that environment punished any mammal that tried to live slowly. So the genes that support long life, the cellular repair mechanisms, the regenerative capabilities, the robust DNA maintenance systems, those got deprioritized. Not because they were useless in principle, but because they were useless in practice. A mouse that could theoretically live 50 years but takes 10 years to reach sexual maturity won't pass on its genes. A mouse that matures in 6 weeks and lives 1 year will fill the world with descendants. This is the core of the longevity bottleneck hypothesis. Dinosaurs didn't directly steal our longevity genes. They created an environment where those genes became liabilities instead of assets. Evidence for this comes from comparisons with reptiles. Tuataras, reptile-like creatures from New Zealand, can live over 100 years and show remarkably slow aging. DNA analysis suggests they retain robust anti-aging genetic pathways that mammals have lost or downregulated. Why? Because Tuatara never went through a 100 million year gauntlet of being small and hunted. They evolved in different circumstances and kept genetic tools we discarded. Aldabra giant tortoises live 150 years or more. One individual, named Jonathan, is approximately 191 years old and still alive. Another, Adwaita, died in 2006 at an estimated 250 years old. These aren't even the record holders. Some reptile lineages show negligible senescence, essentially not aging in any conventional sense. Mammals? We're conspicuously absent from that list. Even the longest-lived mammal, the bowhead whale at 200 plus years, shows clear aging processes. It just ages slowly. It doesn't escape aging entirely like some reptiles appear to. This absence isn't random. It's the signature of our evolutionary past. Now, the dinosaurs are gone. The asteroid that ended the Cretaceous period 65 million years ago wiped out all non-avian dinosaurs. Suddenly, the world belonged to mammals. Ecological niches opened up. Size restrictions lifted. Mammals diversified explosively, filling every available role within a few million years. But we couldn't undo 100 million years of genetic optimization for short lives. Evolution doesn't work backwards. It can't restore complex systems that were lost or degraded over thousands of generations. It can only work with what remains. So mammals evolved longer lifespans than our Mesozoic ancestors, yes. Some mammals got quite large. Some developed sophisticated social structures. Some, like humans, even developed big brains and culture. But we did all of this while dragging the accumulated baggage of the dinosaur era. We age faster than reptiles of comparable size. We lack regenerative abilities that some reptiles retain. Our DNA repair systems, while functional, aren't as robust as they theoretically could be. We're building longevity on a foundation that was optimized for the opposite. Elephants live about 70 years. Respectable, but they weigh 6,000 kilograms. Bowhead whales reach 200 years, but they're aquatic, which changes the rules entirely. Different metabolic demands, different environmental pressures. Land mammals, we top out much lower than you'd expect from our size. And there's another factor. Dinosaurs themselves had a secret weapon that mammals lack: air sacs. Modern birds have complex respiratory systems with air sacs that extend throughout their bodies, even into their bones. These sacs don't just store air. They create a one-way flow through the lungs, making breathing far more efficient. You extract more oxygen per breath. You cool your body more effectively. You can sustain higher activity levels. Dinosaurs had these too. Fossil evidence shows air sac systems in Tyrannosaurus, Apatosaurus, and many other lineages. These respiratory systems likely evolved independently multiple times in different dinosaur groups. They were that advantageous. This innovation helped dinosaurs dominate even when atmospheric oxygen was lower than today. During much of the Mesozoic, oxygen levels were only 10 to 15% compared to 20% now. Yet dinosaurs thrived, grew massive, sustained active lifestyles. Their superlungs compensated. Mammals never evolved this system. We're stuck with bidirectional lungs, breathing in and out through the same pathway. Less efficient. More limiting. Another constraint inherited from our ancestry, this time from our amphibian roots. So when dinosaurs finally disappeared, mammals inherited a world they were biochemically unprepared to dominate in certain ways. We succeeded anyway through different strategies: intelligence, social cooperation, adaptability. We found workarounds for our limitations, but we couldn't escape the fundamental constraints. We still age according to patterns set when we were small and desperate. We still lack regenerative capabilities that some other lineages retain. We still operate within metabolic boundaries shaped by ancient pressures. This is what makes evolutionary history so crucial for understanding biology. The present never makes complete sense without the past. Why do mammals age the way we do? Because dinosaurs. Why don't we regenerate limbs like some salamanders? Because dinosaurs. Why are our lifespans shorter than theoretical predictions based on body size? Because dinosaurs. Every biological trait exists in a historical context. Every feature reflects compromises made by ancestors facing challenges you never experience. Every limitation traces back to some ancient bottleneck, some crisis, some environmental pressure that no longer exists, but whose effects persist. You can't understand human aging without understanding mammalian evolution. You can't understand mammalian evolution without understanding the Mesozoic. You can't understand the Mesozoic without understanding dinosaurs. The chain of causation stretches back unbroken across hundreds of millions of years. And here's the really mind-bending part. Those dinosaurs that shaped our evolution, they're still here, not as fossils, as birds. Every pigeon, every sparrow, every chicken is a living dinosaur. The lineage never actually ended. It just got smaller and diversified. Birds retained the air sac systems, the high metabolisms, the rapid growth patterns. They're still living according to rules set in the Mesozoic, and they still age differently than mammals. A parrot can live 80 years despite weighing less than a kilogram. An albatross can breed successfully into its 60s. Birds, the surviving dinosaurs, never went through our bottleneck. They kept their tools, which raises an unsettling question. If the extinction hadn't happened, if dinosaurs still dominated, would mammals ever have evolved long lifespans at all? Or would we still be small, short-lived creatures hiding in burrows, optimized for rapid reproduction and nothing else? We'll never know. But the fact that we have to ask reveals something profound about contingency and evolution. Your biology isn't inevitable. It's the product of specific historical accidents. Different past, different present. The asteroid that killed the dinosaurs didn't just clear ecological space. It fundamentally changed what was possible for mammals. Human civilization, human technology, human culture, all of it exists downstream of that impact. No asteroid, no age of mammals. No age of mammals, no primates. No primates, no humans. Our entire existence traces back to a rock from space that happened to hit Earth at just the right time. And yet, even after that catastrophic reset, even after 65 million years of mammalian evolution, we still carry marks from the age of dinosaurs. We're still constrained by decisions made in a world we never knew. The past doesn't just influence the present. It structures it, limits it, shapes what's possible and what isn't. This is the deep lesson of evolutionary biology. You are not free. You're embedded in history, carrying forward an inheritance you didn't choose and can't escape. Understanding that inheritance doesn't free you from it, but it does explain why certain changes come easily and others never come at all. Human lifespans have increased dramatically in recent centuries. Better nutrition, medicine, sanitation, all have pushed average lifespans from 30 or 40 years to 70 or 80. But maximum lifespan, that's barely budged. The oldest confirmed human lived to 122. That number hasn't increased despite all our medical advances. Why? Because we're bumping up against constraints set not by modern conditions but by ancient ones. The longevity bottleneck isn't a problem we can solve with better healthcare. It's written into our cellular architecture, into our developmental programs, into the fundamental logic of how mammalian bodies work. We can optimize within those constraints. We can't easily rewrite them, unless we start doing something evolution never did. Unless we start editing the inheritance directly. Gene editing technologies are already here. CRISPR, base editing, prime editing, tools that allow precise modification of DNA sequences. We can already fix single gene diseases, correct mutations, swap out faulty code for functional versions. But longevity isn't controlled by a single gene. It's a system property, emerging from interactions between hundreds of genes, regulatory networks, and developmental programs. You can't just flip one switch and double lifespan. The architecture is too complex, too interconnected. But here's what makes it interesting. We don't need to understand the entire system to start modifying it. We just need to identify key control points, places where small changes produce large effects. And we're starting to find them. The mTOR pathway, which regulates cellular growth and metabolism. The insulin signaling pathway, which controls how cells respond to nutrients. The sirtuin genes, which regulate DNA repair and cellular stress responses. These aren't random targets. They're conserved across species, present in everything from yeast to humans. And when you modify them, lifespan changes. In laboratory organisms, the results are dramatic. Mutant worms with altered insulin signaling live twice as long as normal. Flies with modified mTOR activity show 40% lifespan extension. Mice with extra copies of certain DNA repair genes live 20% longer and stay healthier into old age. These aren't marginal improvements. They're proof that the fundamental limits of aging can be pushed with the right interventions. The question isn't whether it's possible. The question is how far we can push it and what breaks when we do. Because nothing in biology is free. Every adaptation comes with trade-offs. Those long-lived mutant worms, they're smaller, less fertile, slower to develop. The mice with enhanced DNA repair, they're more prone to certain metabolic problems. Evolution optimized for reproduction, not longevity. When you start optimizing for longevity instead, other systems suffer. You're not just extending life, you're restructuring the entire balance of biological priorities. This is where it gets complicated. Human biology isn't like worm biology. We're not going to accept being smaller, less fertile, and metabolically compromised just to live longer. Any intervention has to preserve function, maintain quality of life, keep the organism viable across multiple dimensions. That's a much harder problem than just extending lifespan in a lab dish. You need to understand not just what controls aging, but how aging integrates with everything else the body does. And we're nowhere near that level of understanding yet. We know some of the players, some of the pathways, some of the mechanisms, but the full picture, the complete map of how all these systems interact, how they respond to perturbation, how they maintain stability across decades, that's still being worked out. Every new study reveals more complexity, more feedback loops, more unexpected connections. The system is deeper than anyone anticipated. Which brings us back to the bottleneck. Those genes we lost, those systems we abandoned during the Mesozoic, they're not just sitting in some junk DNA waiting to be reactivated. They're gone, deleted, mutated beyond recognition, or repurposed for other functions. We can't just restore them. We'd have to rebuild them from scratch, reverse engineering capabilities that evolution discarded 100 million years ago. That's not impossible. But it's not straightforward either. Consider what we'd be trying to recreate. Robust DNA repair mechanisms that maintain genomic stability across centuries. Regeneration systems that can rebuild damaged tissues without triggering cancer. Metabolic regulation that prevents accumulation of cellular damage. These aren't simple traits. They're complex, integrated systems involving dozens of genes working in concert. And they have to be compatible with everything else human cells do. You can't just copy the genes from a turtle and paste them into human DNA. The cellular context is different. The regulatory environment is different. What works in one species might be toxic in another. But let's say we figure it out. Let's say we identify the key missing pieces, design synthetic versions compatible with human biology, and successfully integrate them. What happens then? Do we suddenly start living 200 years like bowhead whales? Do we stop aging altogether like certain jellyfish that can reverse their life cycle? Or do we just push the limit from 120 to 150? gaining a few extra decades before hitting some other constraint we haven't identified yet. Nobody knows. We've never tried this before. Every intervention so far has been in model organisms with much simpler biology than humans. Translating those findings into actual human therapies is a massive leap. And even if the therapies work, even if we successfully extend maximum lifespan, we're not just changing how long people live. We're changing society, economics, culture, everything built on the assumption that humans have a certain natural lifespan. Think about retirement. The entire system assumes you work for 40 years, then retire for 20 or 30. What happens when people live to 150? Do they work for 80 years? Do retirement ages shift to 90? Or do we completely restructure how work, leisure, and economic production are organized? And that's just one institution. Every aspect of society, from education to healthcare to family structure, is calibrated around current human lifespans. Change the lifespan, and everything else has to change too. Then there's the question of access. Gene editing therapies aren't going to be cheap, at least not initially. If longevity treatments exist, but only the wealthy can afford them, you're not just extending life. You're creating a biological class divide. The rich live 150 years, accumulate wealth and power across multiple generations, while the poor die at 80. That's not a minor inequality. That's a fundamental restructuring of human society along biological lines. And history suggests those kinds of divides don't resolve peacefully, even if access becomes universal. Even if everyone can get longevity treatments, you're still facing massive demographic shifts. Populations age, birth rates decline, the ratio of old to young shifts dramatically. Right now, the elderly are a minority supported by a larger working age population. Flip that ratio, and the entire economic model breaks. Who's producing goods? Who's innovating? Who's taking risks? Societies run on young people. Change the age structure, and you change how societies function at a fundamental level. And we haven't even touched on the psychological implications. Human psychology is built around the fact that life is finite. We make decisions, form relationships, pursue goals, all within the context of limited time. What happens when that context changes? Do people become more cautious, less willing to take risks when they have centuries ahead of them? Or do they become more reckless, figuring they have plenty of time to recover from mistakes? Does meaning change when life is no longer scarce? These aren't hypothetical questions. They're the immediate consequences of successfully defeating the longevity bottleneck. And they're why this isn't just a scientific problem. It's a philosophical, ethical, and political problem wrapped in a biological package. You can't separate the science from the implications. Any attempt to extend human lifespan is also an attempt to redesign human society. But let's go deeper. Let's talk about what we'd actually be changing at the cellular level. Aging isn't one process. It's several overlapping processes, each contributing to decline. Cellular senescence, where cells stop dividing and start secreting inflammatory factors. Telomere shortening, where the protective caps on chromosomes erode with each cell division. Mitochondrial dysfunction, where the cell's energy factories start producing more waste and less power. Protein aggregation, where misfolded proteins accumulate and gum up cellular machinery. Each of these is a separate problem requiring separate solutions, and they interact. Senescent cells promote inflammation, which damages mitochondria, which produces oxidative stress, which causes more DNA damage, which triggers more senescence. It's a cascade, each problem feeding into the others, accelerating decline. Breaking the cascade at one point might slow aging, but it won't stop it. You need to address multiple points simultaneously. That's why single interventions only produce modest lifespan extensions. The system has redundancy built in. Evolution didn't want organisms aging out too quickly, but it also didn't prioritize extreme longevity. The result is a system that degrades gradually through multiple parallel mechanisms. Reversing that requires coordinated intervention across all those mechanisms. Enhanced DNA, repair to reduce mutation accumulation, clearance of senescent cells to reduce inflammation, mitochondrial rejuvenation to maintain energy production, protein quality control to prevent aggregation. Each of these is an active area of research. Each has shown promise in animal models. But combining them, getting them to work together without interfering with each other, that's the real challenge. And even if you solve the technical problems, you're still left with the question of timing. When do you start these interventions? In childhood, before damage accumulates. In middle age, when decline begins. In old age, trying to reverse damage already done. Each approach has different risks and benefits. Start too early, and you might disrupt normal development. Start too late, and the damage might be irreversible. The window matters. Current thinking suggests middle age is the sweet spot. Old enough that you're not interfering with growth and development. Young enough that damage hasn't become overwhelming. But that's speculative. We won't know until we try. And trying means human trials, which means accepting that early attempts will be imperfect, potentially harmful, definitely unpredictable. Someone has to be first. Someone has to take the risk of being the test case for interventions that might work brilliantly or fail catastrophically. This is the frontier, not just of science, but of human experience. We're talking about fundamentally altering what it means to be human, to age, to die. And we're doing it without a map, guided only by fragmentary knowledge of how biology works and incomplete understanding of what happens when you start changing fundamental parameters. It's exhilarating and terrifying in equal measure. The dinosaur bottlenecks set our baseline. It determined our starting point, our constraints, our inherited limitations. But it didn't determine our end point. Technology gives us options evolution never provided. We can bypass the slow generational process of natural selection and make changes directly, deliberately, with intent. That's unprecedented power. And like all power, it comes with responsibility and risk. So here we are, standing at a threshold. Behind us, 100 million years of mammalian evolution, shaped by the shadow of dinosaurs. Ahead, an uncertain future where we might transcend those ancient constraints or discover new ones we didn't anticipate. The science is moving fast, the implications are sprawling, and the decisions we make in the next few decades will echo through centuries. Human lifespan might be about to change dramatically, or it might hit new barriers we haven't discovered yet. Either way, we're running an experiment with ourselves as the subject, and unlike lab animals, we can't just discard the results if they don't work out. We have to live with them, literally. The dinosaurs themselves tell a story we barely paid attention to until recently. For 165 million years, they dominated every terrestrial ecosystem on the planet. That's not just dominance, that's geological scale success. They appeared around 245 million years ago during the Middle Triassic, became the dominant land vertebrates after the Triassic-Jurassic extinction event 201 million years ago, and held that position through the entire Jurassic and Cretaceous periods. During all that time, mammals existed. They scurried around dinosaur feet, barely larger than domestic cats, mostly nocturnal, entirely constrained. Here's what makes this relevant. Those mammals weren't just small because they lacked opportunity. They were small because anything larger got eaten. They were nocturnal because daytime belonged to predators they couldn't outrun. They were short-lived because survival to old age was statistically improbable when you're prey. And that went on for 100 million years. Not 1,000 years. Not 1,000,000. 100 million. That's enough time for evolution to completely rewrite a genetic playbook. Think about what gets selected for in that environment. Fast maturation, rapid reproduction, high offspring numbers, organisms that reach sexual maturity quickly, and produce many descendants before something eats them. What doesn't get selected for? Longevity. Robust DNA repair mechanisms. Extensive regenerative capacity. All the cellular machinery that enables long lifespan becomes unnecessary weight. Genes that maintain those systems stop being advantageous. They might even become disadvantageous if they divert resources from reproduction. So they disappear. Not immediately, not in one generation, but over millions of years, through countless reproductive cycles. The genetic toolkit for extreme longevity gets dismantled piece by piece. That's the longevity bottleneck hypothesis. It explains something that puzzled biologists for decades. Why are mammals so bad at aging compared to reptiles? Why does a turtle live 150 years while an elephant, vastly larger and more complex, barely reaches 70? Why can a bowhead whale hit 200 years? But that's the absolute ceiling for mammals, while being routine for some reptiles. Because reptiles didn't go through the bottleneck. They weren't prey for 100 million years. They didn't face the same evolutionary pressure to prioritize speed over durability. Some of them, the ones that survived, kept their longevity genes. Tuataras live over 100 years and age remarkably slowly. Their DNA analysis shows they retained anti-aging mechanisms mammals lost. Giant tortoises reach 150, sometimes more. One Aldabra tortoise lived 250 years. These aren't freak occurrences. They're the baseline for organisms that didn't have longevity selected out of them. Mammals are conspicuously absent from the list of negligibly senescent species. Animals that show minimal aging. That's not coincidence. That's evolutionary history written in our genes. But wait, if the bottleneck stripped out longevity genes, how do humans live 70 plus years? How do elephants reach similar ages? How did we recover any longevity at all? We didn't recover it, we rebuilt it, differently. After the dinosaurs went extinct 65 million years ago, mammals exploded into every available niche. They got bigger, they got more diverse, and some lineages, particularly primates and certain large herbivores, started evolving longer lifespans again. But they did it under constraints. They couldn't just reactivate the old reptilian longevity systems because those genes were gone or broken. They had to work with what remained, jury-rigging new solutions from existing parts. That's why mammalian longevity looks different from reptilian longevity. It's built on a different foundation, less robust, more prone to specific failure modes, and it hits walls that reptiles don't encounter because we're using different biological mechanisms to achieve similar outcomes. Humans are weird, even by mammalian standards. We live much longer than our body size predicts. Most mammals follow a fairly predictable curve relating body mass to lifespan. Larger animals generally live longer, but humans are massive outliers. We live 2 to 3 times longer than mammals of similar size. That required specific genetic changes, most of which happened relatively recently in evolutionary terms. Within the last few million years, those changes didn't restore what the bottleneck removed. They compensated for it. Enhanced certain repair mechanisms, improved cellular quality control, extended the functional period of various organ systems, but all while working within the constraints established during those 100 million years of being dinosaur snacks. Which brings us back to the dinosaurs themselves. How long did they actually live? Turns out, not as long as anyone expected. Early estimates for large sauropods, the massive long-necked herbivores, suggested lifespans of 200 or even 300 years. That was based on comparison with modern crocodiles and tortoises, which have slow metabolisms and extended lifespans. But bone histology, the study of growth rings in fossilized bones, completely overturned those estimates. Apatosaurus and Diplodocus probably lived 70 to 80 years, about the same as a modern elephant. Tyrannosaurus rex lived around 30 years, maybe reaching 40 at maximum. These aren't ancient, slowly aging reptiles. They're fast-living, rapidly growing animals with comparatively short lives. Why? Metabolism. Dinosaurs weren't cold-blooded like modern reptiles. They weren't warm-blooded like modern mammals either. They were something in between, a metabolic strategy called mesothermy. Their metabolic rates were higher than reptiles, but lower than most mammals. Some lineages, particularly the theropods and sauropods, had metabolic rates comparable to modern birds, which are extremely high. Higher than mammals in some cases. That enabled incredible growth rates. A Tyrannosaurus rex reached full size, 8,000 kilograms, in just 15 to 18 years. A Apatosaurus hit 25,000 kilograms in about 15 years. That's a growth rate exceeding 5,000 kilograms per year. For comparison, elephants take 30 to 40 years to reach their maximum size of around 6,000 kilograms. Dinosaurs grew faster and bigger than anything alive today, but fast growth has costs. High metabolism means high cellular turnover. Rapid cell division accumulates more replication errors, more oxidative stress, more wear on cellular machinery, all the things that drive aging. Dinosaurs burned bright and fast, then died relatively young despite their enormous size. They also had another advantage we're only starting to appreciate. Air sacs. Like modern birds, many dinosaurs had complex respiratory systems, with air sacs extending from their lungs into their bones. This made them lighter, which saved energy. But it also made oxygen exchange vastly more efficient. At a time when atmospheric oxygen was only 10 to 15% compared to today's 20%. Having super-efficient lungs was a massive advantage. It let them sustain activity levels mammals couldn't match at similar sizes. This system evolved independently at least 3 times in different dinosaur lineages. Convergent evolution. When the same trait appears repeatedly in separate groups, that usually means it's solving a critical problem. In this case, the problem was scaling. How do you build an animal weighing 30 tons that can still move, breathe, and function? Air sacs were part of the answer, but none of this made them immortal, or even particularly long-lived by the standards we might expect for their size. They grew explosively, dominated their environments completely, reproduced prolifically, and died while still relatively young. Many dinosaurs died while still growing, which is unusual. Most mammals reach adult size and then live for additional years. Dinosaurs often didn't make it that far. Why? Probably reproduction strategy. Dinosaurs laid large clutches of eggs, dozens at a time in some species. That's a huge reproductive output compared to mammals, which typically have small litters or single births. When you're producing that many offspring, natural selection doesn't reward longevity as strongly. Your genes are already in the next generation. Living longer provides diminishing returns. Contrast that with elephants or whales. They reproduce slowly. Few offspring, long gestation periods, extended parental care. In that context, living longer is advantageous. You can raise more offspring over your lifetime. Natural selection favors longevity because it increases reproductive success. Different strategies, different outcomes, and for mammals trapped under dinosaur dominance, only one strategy was viable. Reproduce fast, die young. Don't invest in systems you won't live long enough to use. The genetic consequences of that strategy are still with us. We carry the scars of the bottleneck in every cell. Shortened telomeres compared to reptiles. Less efficient DNA repair in certain pathways. Reduced regenerative capacity in most tissues. These aren't random features. They're the legacy of 100 million years of evolutionary pressure for rapid turnover. Some researchers argue we lost specific genes entirely, whole pathways for cellular maintenance that reptiles still possess. Others think the genes remain, but are inactivated, silenced by regulatory changes that accumulated over time. Either way, the result is the same. We're working with a reduced toolkit compared to our pre-bottleneck ancestors. And this matters for modern longevity research because it defines what's possible versus what's fantasy. You can't simply turn back the clock to a state that never existed. Humans were never long-lived reptiles with negligible senescence. Our lineage went through the bottleneck. That's our starting point. Any intervention has to work within that framework or actively compensate for what was lost, which is harder than it sounds. Take regeneration. Some reptiles can regrow entire limbs. Mammals can't, with very limited exceptions like fingertip regeneration in children. That's not because mammalian cells lack the information to build limbs. Every cell has the complete genome. It's because the regulatory networks controlling that process were dismantled during the bottleneck. The genes exist, but the switches are broken. Fixing that means understanding not just which genes are involved, but how they're coordinated, when they're activated, how they interact with surrounding tissues, and then figuring out how to reactivate processes that haven't functioned properly in 100 million years. Some labs are attempting this. Results so far are modest. A bit of cartilage regrowth here, some nerve regeneration there, nothing approaching full limb regeneration. The complexity is staggering. Or consider cellular senescence, the accumulation of non-dividing cells that secrete inflammatory factors. This process is tightly linked to cancer prevention. Cells that detect damage stop dividing to prevent mutations from spreading. That's good. But those senescent cells accumulate over time and create chronic inflammation. That's bad. Clearing them improves health span in mice, but doing it safely in humans means not disrupting the cancer prevention mechanism they're part of. Reptiles handle this differently. Their cellular quality control systems appear more robust. They accumulate senescent cells more slowly. When they do accumulate them, the inflammatory response is less severe. Why? Probably because they retained longevity-associated genes mammals lost. Genes we can identify by comparing genomes but can't easily transfer or reactivate. The bottleneck doesn't make extended longevity impossible. It just makes it harder. We're climbing uphill against evolutionary history. Every intervention has to account for the fact that our biology wasn't optimized for the lifespans we're trying to achieve. We're pushing systems beyond their design parameters, which means unexpected failures become more likely. But here's the thing. Evolutionary constraints aren't absolute limits. They're starting conditions. We didn't evolve to fly, but we built airplanes. We didn't evolve to survive underwater, but we built submarines. Technology lets us transcend biological limitations. The question isn't whether we can extend human lifespan beyond what evolution provided. We already have. Average lifespan doubled in the past century through medicine and public health. The question is how much further we can push it and what breaks along the way. Which brings us to one of the strangest comparisons in biology. Dinosaurs versus mammals. Specifically, why creatures weighing 8 tons died younger than animals a tenth their size. Consider Tyrannosaurus rex, 8,000 kilograms of apex predator. Recent studies using bone histology show they lived around 30 years, maybe pushing 40 in exceptional cases. That's it. An African elephant weighing roughly half as much can reach 70 years. Asian elephants sometimes hit 80. The oldest confirmed was 89. So the elephant, despite being smaller, lives more than twice as long. Gets weirder with whales. Bowhead whales can exceed 200 years. Some estimates push 211. That's 7 times the lifespan of T-Rex in an animal that's significantly larger. Blue whales, the largest animals ever to exist, live 80 to 90 years minimum, possibly longer. We're still figuring out their maximum age because they outlive research programs. So what's happening here? Why didn't size translate to longevity for dinosaurs the way it does for modern mammals? The answer involves metabolism. Dinosaurs weren't cold-blooded like modern reptiles. They weren't warm-blooded like mammals either. They occupied this middle ground scientists call mesothermy. Their metabolic rates were higher than reptiles, but generally lower than mammals. Except that's not universally true. Some dinosaur lineages, particularly theropods and sauropods, had metabolic rates comparable to modern birds. In some cases, higher than mammals, which created a problem. High metabolism means rapid growth. Rapid growth means reaching reproductive age quickly, but it also means burning through your biological resources faster. T-Rex grew explosively, 15 to 18 years from hatchling to full size. That's a hip height of 3 meters, length of 11 meters, mass between 5 and 8 tons. All in less than 2 decades. Compare that to Dinosaurs, a giant crocodile from the Cretaceous period. Similar length to T-Rex, around 10 to 11 meters. But Dinosaurs took nearly 50 years to reach that size. Same dimensions, radically different timeline. The crocodile grew slowly with a reptilian metabolism. The dinosaur grew fast with something closer to a mammalian or avian metabolism. That speed came with costs. Fast growth requires intense cellular activity. More cell divisions mean more opportunities for errors. More metabolic activity generates more oxidative stress. The machinery wears out faster. Dinosaurs were essentially running their biology at higher RPMs than modern reptiles, which meant components failed sooner. Sauropods show this even more dramatically. Apatosaurus reached 25,000 kilograms in about 15 years. That's a growth rate exceeding 5,000 kilograms per year at peak. Alamosaurus hit 32,000 kilograms within 45 years. These animals were adding mass at rates comparable to rapidly maturing birds and large mammals. Yet their final lifespans, based on bone analysis, probably didn't exceed 70 or 80 years. About the same as a modern elephant, despite being 10 times heavier. Early paleontologists thought the biggest dinosaurs lived for centuries. Made sense, right? Huge body, long life. Estimates of 300 years for large sauropods were common. Those estimates were based on comparisons with crocodiles and turtles, which have slow metabolisms and can live extremely long lives. Aldabra giant tortoises reach 150 years routinely. One individual, Adwaita, possibly lived 250 years. Another, Jonathan, is currently around 191 years old, so the logic seems sound. But bone histology changed everything. Growth rings in dinosaur bones, laid down like tree rings, revealed the truth. Most dinosaurs died young, sometimes while still growing. The rings showed rapid early growth, followed by a slowdown as they approached adult size. Then death relatively soon after. They didn't have the long post-maturity phase that elephants or whales enjoy. Why? Probably reproduction. Many dinosaurs produce large clutches of eggs, dozens at a time. That's a massive reproductive output in a short period. Contrast that with elephants and whales, which reproduce slowly. One offspring every few years. Long gestation periods, extended parental care. That reproductive strategy favors longevity. You need to survive long enough to raise multiple offspring to maturity. Natural selection rewards mechanisms that keep you alive longer. Dinosaurs played a different game. Produce many offspring quickly, let most of them die. Ensure a few survive through sheer numbers. That strategy doesn't require the parents to stick around for decades. Once you're reproductively mature and have successfully bred, there's less selective pressure for extended lifespan. Your genes are already in the next generation. The metabolic trade-off matters here too. High metabolism enables rapid growth and high activity levels. Dinosaurs were likely more active than modern reptiles. Their respiratory systems, with bird-like air sacs extending into their bones, provided extremely efficient oxygen delivery. This system allowed them to sustain activity levels mammals of similar size would struggle with. The air sacs also served as cooling mechanisms and reduced weight, making massive bodies more feasible. But efficient respiration and high activity come at a cost. More oxygen consumption means more free radicals, more cellular damage, faster accumulation of the molecular wear and tear that drives aging. Birds, which inherited this respiratory system from their dinosaur ancestors, have relatively short lifespans for their metabolic rates. A parrot might live 50 years, which seems long, but it's short compared to what you'd expect from their slow heart rates and low body temperatures during rest. They're paying the metabolic price of their efficient but demanding respiratory system. Dinosaurs face the same trade-off. Their advanced respiratory systems let them dominate terrestrial ecosystems for 165 million years. That's an extraordinary run. Mammals, during that entire period, stayed small, rarely exceeding the size of a house cat, mostly nocturnal, mostly eating insects. The dinosaurs owned the planet, but individual dinosaurs didn't live particularly long, which creates an interesting parallel with the longevity bottleneck. During those 165 million years, mammals were under constant pressure to reproduce quickly and die young. Living long provided no advantage when you were likely to be eaten within a few years anyway. The genes and pathways supporting extended longevity atrophied or disappeared. Mammals emerged from the bottleneck with reduced longevity potential compared to reptiles. But here's what's strange. Modern mammals, despite going through that bottleneck, now live longer than dinosaurs did. Elephants outlive T-Rex. Whales dramatically outlive any dinosaur. How? Because after the dinosaurs disappeared, mammals had 65 million years to re-evolve longevity. But they did it differently than reptiles. Reptilian longevity relies on negligible senescence. They age so slowly that external factors, disease, predation, starvation, kill them before aging does. Some show no increase in mortality rate with age at all. That's what the bottleneck cost us. Mammalian longevity uses different mechanisms: better DNA repair, more robust immune systems, tumor suppression pathways that prevent cancer. Mammals get old. We age, obviously and progressively, but we've evolved ways to postpone the consequences, to keep critical systems functioning despite accumulating damage. It's not elegant like reptilian negligible senescence, but it works. Large mammals, in particular, evolved additional tricks. Better cancer suppression, because large bodies have more cells and more cell divisions, creating more cancer risk. Elephants have multiple copies of the TP53 gene, which detects and destroys damaged cells before they become tumors. Bowhead whales have mutations in genes involved in DNA repair and cell cycle regulation that improve their resistance to age-related diseases. These adaptations took millions of years to evolve. They're specific solutions to specific problems faced by large, long-lived mammals, and they happened after the bottleneck, which means we have the capacity to evolve longevity mechanisms, but we're starting from a disadvantaged position compared to reptiles. We can't access the same toolkit they use. This matters for longevity research because it defines the problem space. If you want to extend human lifespan, you're working with mammalian biology. That means dealing with progressive senescence, accumulating cellular damage, inflammatory responses that get worse over time. You can't just flip a switch and activate reptilian negligible senescence. Those systems don't exist in our genome. They were lost or never developed, but you might be able to borrow specific components. CRISPR gene editing could, theoretically, introduce enhanced DNA repair genes from long-lived species into human cells. Bowhead whale mutations that reduce cancer risk. Naked mole rat mechanisms that prevent protein misfolding. These are all active areas of research. Results so far are preliminary but promising. The challenge is integration. You can't just paste a whale gene into a human genome and expect it to work. Genes operate within networks. They interact with other genes, with regulatory elements, with cellular machinery that evolved alongside them. Introducing foreign genetic elements creates compatibility problems. The new gene might not express properly. It might interact with existing genes in unexpected ways. It might solve one problem while creating 3 others. Some researchers are trying a different approach. Instead of introducing new genes, activate existing ones that are currently suppressed. Humans have many of the same genes that long-lived reptiles use. They're just not active or not active enough. If you can identify the regulatory mechanisms controlling those genes, you might be able to turn them back on without introducing foreign DNA. That's cleaner from a compatibility standpoint, but requires understanding regulatory networks that are staggeringly complex. Others focus on removing damage rather than preventing it. Cellular senescence, as mentioned earlier, accumulates with age. These non-dividing cells secrete inflammatory factors that damage surrounding tissue. Drugs called senolytics can selectively kill senescent cells. In mice, this improves health span dramatically, reduces inflammation, restores tissue function. Human trials are underway. Early results suggest it's safe and shows some benefit, but we're far from understanding optimal dosing or long-term effects. Then there's the metabolic angle. Restricting calorie intake extends lifespan in nearly every organism tested. Yeast, worms, flies, mice. The effect size varies, but the trend is consistent. Eat less, live longer. Why? Probably because it reduces metabolic stress. Lower calorie intake means less oxidative damage, fewer free radicals, less cellular wear and tear. It's like running your engine at lower RPMs. Components last longer. But severe calorie restriction isn't practical for humans. People don't want to be hungry all the time. So researchers are looking for drugs that mimic the metabolic effects of calorie restriction without requiring you to actually eat less. Compounds like rapamycin, metformin, and resveratrol show promise. They activate some of the same cellular pathways that calorie restriction does. Whether they actually extend human lifespan remains to be seen. The trials take decades. What all these approaches have in common is they're working around the bottleneck, compensating for what was lost, trying to rebuild longevity mechanisms that our ancestors discarded 100 million years ago because they didn't provide survival advantage when dinosaurs ruled the planet. It's possible. Evolution isn't destiny, but it's harder than if we'd retained those mechanisms all along. Here's the thing. Nobody tells you about evolutionary bottlenecks. They don't just limit what you can become. They define what you can never go back to being. Mammals evolved explosive reproductive strategies because they had to. When you're the size of a mouse and everything wants to eat you, longevity is worthless. Fast reproduction is survival. And that strategy worked. We survived the dinosaurs. We inherited the Earth. But we paid a price. Consider what dinosaurs actually were. Not what popular culture makes them. What the fossil record shows. They ruled the planet for 165 to 180 million years. That's not a typo. From the Middle Triassic until the end of the Cretaceous. 165 million years of dominance. Compare that to mammals. Modern mammals have only existed for about 65 million years. We've been dominant for maybe 2 million if you're generous with the definition. Dinosaurs had more than 80 times our entire tenure as a major group just to perfect their reign. That's staying power on a scale that's hard to comprehend. During that time, mammals existed. We were there, scurrying in the shadows, rarely bigger than a house cat, mostly rodent-sized, nocturnal, prey animals for 100 million years. That's twice as long as the entire age of mammals from the extinction event until now. Think about that timescale. 100 million years of evolutionary pressure saying one thing: reproduce fast, die young, Don't waste resources on longevity you'll never use. Every generation that survived was the one that hit sexual maturity quickest, had the most offspring, didn't invest in long-term maintenance because there was no long-term. A mammal living past 2 or 3 years during the Mesozoic was an evolutionary dead end. Their genes didn't propagate. The fast breeders won. And they won so consistently for so long that the genetic architecture of longevity was dismantled piece by piece, not because it was actively harmful, because it was expensive to maintain and provided zero benefit. Now look at what dinosaurs were doing during that same period. Growing slowly, living longer, investing in body size and metabolic efficiency. Tyrannosaurus rex took 15 to 18 years just to reach full size. That's longer than many mammals live today. And T-Rex probably lived to around 30 years old, maybe longer. Some recent studies suggest they didn't hit maximum size until 35 to 40. That's a fundamentally different life strategy. Slow growth, extended lifespan, large body mass. Sauropods were even more extreme. Apatosaurus reached 25,000 kilograms in about 15 years. That's over 5,000 kilograms of growth per year at peak. Absolutely explosive by reptile standards, but still slower than you'd think for something that large. And after reaching full size, they lived another 30, 40, maybe 50 years. That's a 70 to 80-year lifespan total. About the same as a modern elephant, except sauropods were 10 times heavier. Scientists used to think the biggest dinosaurs lived for hundreds of years. Early estimates put sauropods at 300 years based on comparisons with crocodiles and turtles. But bone histology proved otherwise. Growth rings in fossilized bones, laid down like tree rings, reveal actual ages. And they show most dinosaurs died relatively young by reptile standards. Not ancient, not centenarian, just modestly long-lived compared to mammals. Why didn't they live longer? They had the size. They had the metabolic capacity. Some had metabolic rates comparable to modern birds, higher than mammals. They had advanced respiratory systems with air sacs invading their bones, making them lighter and more efficient. They dominated every terrestrial ecosystem on the planet. What stopped them from living 200 years like bowhead whales do now? Reproduction strategy. Dinosaurs laid eggs, lots of eggs, large clutches, many offspring in short periods. That's a fast reproduction strategy hiding inside a large body. If you're producing dozens of offspring per breeding season, there's less evolutionary pressure to live 200 years. You've already propagated your genes extensively by age 50. Living longer provides diminishing returns. Contrast that with elephants. They reproduce slowly, one calf every few years, long gestation, extended parental care. For them, living 70 years makes sense. More reproductive opportunities, more chances to pass on genes. Bowhead whales live 200 years and reproduce even slower. One calf every 3 to 4 years, maybe 30 offspring in a lifetime if they're lucky. For that strategy, extreme longevity is essential, but it requires a complete metabolic and cellular architecture built around damage prevention and repair. Dinosaurs never built that. They didn't need to. Their strategy worked without it. And here's where it connects back to us. Mammals inherited a world without dinosaurs. Suddenly there was ecological space. Niches opened. Body size became advantageous again. We got bigger, some lineages much bigger. Whales, elephants, giant ground sloths. But we still carried the genetic legacy of 100 million years spent small and short-lived. The longevity mechanisms that reptiles maintained, we'd already lost. We had to rebuild lifespan extension from scratch, working within the constraints of our existing genetic architecture. That's why the longest-lived mammals don't live as long as the longest-lived reptiles. Jonathan, an Aldabra giant tortoise, is 191 years old. Another of his species, Ada whita, supposedly lived 250 years. Tuatara can exceed 100 years and show almost no signs of aging. Their DNA repair mechanisms, their cellular maintenance systems, they're still intact. Mammals lost those or never developed them to the same degree. We're working with different tools. Bowhead whales are the exception. 200 plus years. Maybe 211 confirmed. They evolved specific genetic mutations that reduce cancer risk and improve DNA repair. But they did it within mammalian constraints. They can't do negligible senescence like some reptiles. They still age, just slowly. And it took them tens of millions of years of evolution in a stable ecological niche to get there. Humans have been around in our current form for maybe 300,000 years. We've had agriculture for 10,000, industrial medicine for 200. We haven't had evolutionary time to develop extreme longevity naturally. We're trying to do it technologically instead. Which brings us back to the question, can we overcome the bottleneck? Can humans extend lifespans significantly despite our evolutionary history? The answer is probably yes, but it's complicated. We're not going to suddenly develop negligible senescence. That would require rewriting fundamental aspects of our biology. But we might extend health span, keep people healthy longer, delay the onset of age-related diseases, push average lifespan from 80 to 100, maybe 120. That's achievable with current research directions. Senolytics eliminate damaged cells that accumulate with age. In mice, this works remarkably well. Inflammation drops, tissue function improves, health span extends. Human trials are showing promise. We don't know yet if it extends maximum lifespan or just improves quality of life. But even just improving quality of life would be significant. Most people don't want to live to 120 if it means 40 years of decline. They want to be healthy at 90. That's the real goal. Caloric restriction mimetics try to capture the benefits of eating less without actually restricting calories. Rapamycin, metformin, resveratrol. They activate cellular stress response pathways that improve maintenance and repair. Does it work in humans? We're not sure yet. The trials take decades because you have to wait for people to age. But animal studies are encouraging. And the compounds are relatively safe. Low risk, potential high reward. What's Gene therapy might introduce specific longevity-associated genes from other species. Bowhead whale mutations, naked mole rat cancer resistance. It's theoretically possible with CRISPR. The challenge is integration. You can't just paste a foreign gene into a human genome and expect it to work correctly. Genes operate in networks. They have regulatory elements. They interact with other genes in ways we don't fully understand. Early attempts might cause more problems than they solve. But as our understanding improves, targeted genetic modifications could become feasible. There's also the approach of activating dormant genes. Humans have many of the same longevity-associated genes that long-lived animals use. They're just not expressed at the same levels, or not active in the same contexts. If we can identify the regulatory switches controlling those genes, we might turn them on without introducing foreign DNA. That's cleaner, safer, more likely to work. But it requires understanding regulatory networks of enormous complexity. Then there's the question of whether we should. Extending human lifespan has societal implications. Population growth, resource consumption, economic systems built around retirement at 65. If people routinely live to 120, do they work until 90? Can pension systems handle that? What about generational wealth transfer, environmental impact? These aren't just technical problems, they're social and ethical ones, and they don't have easy answers. Some argue we should focus on health span, not lifespan. Keep people healthy and functional as long as possible, then have a relatively quick decline at the end. Compression of morbidity, that's probably more valuable than just adding years of frailty. Others say lifespan, and health span are linked. If you're fixing the underlying mechanisms of aging, both improve together. You can't separate them cleanly. The dinosaur connection matters because it reminds us that evolution isn't about perfection. It's about what works in a specific context. Dinosaurs lived a long time because their ecology and reproductive strategy made that advantageous. Mammals evolved fast reproduction and shorter lifespans because that's what worked when dinosaurs were trying to eat us. Neither strategy is objectively better. They're different solutions to different problems, and now we're trying to change our solution without changing the problem. We want longevity, but we're not facing the selective pressures that would naturally produce it. That's the paradox of modern medicine. We're trying to override evolution, and sometimes we succeed. Vaccines eliminated diseases that killed millions. Antibiotics turned deadly infections into minor inconveniences. Surgical techniques saved lives that would have been lost 100 years ago. We've already extended average lifespan dramatically. In 1900, life expectancy was under 50. Now it's close to 80 in developed countries. We added 30 years in a century. That's unprecedented. But we did it by fixing external problems: sanitation, nutrition, preventing infectious disease, treating acute conditions. Those are relatively straightforward. Aging is different. It's not one thing you can fix. It's a constellation of processes that accumulate over decades, and they're baked into our biology at a fundamental level. Fixing aging means re-engineering the system, not just patching holes. Can we do it? Maybe. We're certainly going to try. The amount of money and research effort going into longevity science right now is staggering. Biotech companies, academic labs, wealthy individuals funding moonshot projects. Everyone wants more time. Whether we succeed depends on how deep the constraints go. If the bottleneck is absolute, if mammalian biology simply can't support radically extended lifespans without complete redesign, we'll hit a wall. But if there's flexibility, if we can work within the existing framework and make incremental improvements, we might add decades to human life. Either way, we're living through a unique moment. The first time in history a species is consciously trying to extend its own lifespan using technology. Not waiting for evolution, not accepting the hand we were dealt, actively intervening in our own biology. That's either brilliant or hubris. Probably both. And the outcome will define what it means to be human for generations to come. All because 65 million years ago, a rock fell from the sky and the dinosaurs didn't make it. But we did. And now we're trying to reclaim what they had. Time. Just a little more time. The asteroid that ended the dinosaurs didn't just clear ecological space. It reset the rules. For 100 million years, being a mammal meant being small, fast breeding, and short-lived. That wasn't a choice. It was the only viable strategy when everything larger than a bread box got eaten. And 100 million years is enough time for evolution to completely rewire your biology around that strategy. The genes for extreme longevity, the cellular machinery for negligible senescence, the regenerative capabilities that some reptiles still possess, those got stripped out piece by piece because they provided zero survival advantage when your life expectancy was measured in months. We're still living with that legacy. Every human who's ever aged, every wrinkle, every grey hair, every cellular breakdown, it traces back to ancestors hiding from dinosaurs in the darkness. That's not metaphor. That's actual evolutionary history written into our genome. The longevity bottleneck isn't something that happened to us. It is us. Our biology was forged in that crucible, and we can't simply undo it by wishing or even by clever genetic engineering. But here's what makes it interesting. Dinosaurs themselves, for all their dominance, for all their evolutionary success, didn't live particularly long either. Tyrannosaurus rex, 30 years. Apatosaurus, 70 or 80. These weren't ancient, slowly aging reptiles. They were fast-growing, metabolically intense animals that burned bright and died relatively young. They dominated Earth for 165 million years, not because individuals lived forever, but because their strategy worked. Fast growth, high metabolism, prolific reproduction. The species thrived even as individuals came and went, which reveals something fundamental about evolutionary success. It's not about individual longevity, it's about what works in context. Dinosaurs worked in their context. Mammals under dinosaur rule worked in theirs. And now we're trying to work in a context that no longer exists, trying to extend lifespans beyond what our biology was optimized for, using tools evolution never provided. Can we do it? Probably, to some degree. Senolytics clearing damaged cells, caloric restriction mimetics improving metabolism, gene therapies borrowing tricks from long-lived species. We're already extending average lifespan. The question isn't whether we can push further, it's how far before we hit constraints we can't engineer around. Because those constraints are real. We're not reptiles with negligible senescence. We can't just reactivate systems that were lost 100 million years ago. We're mammals with mammalian biology, carrying mammalian limitations. We can optimize within that framework. Improve DNA repair, reduce inflammation, delay cellular senescence. But we're not going to suddenly start living 200 years like tortoises unless we fundamentally rebuild what it means to be human at a cellular level. And maybe that's okay. Maybe the goal isn't to live like a tortoise. Maybe it's to live like us, just better. Healthier at 90, functional at 100, maintaining quality of life instead of just adding years of decline. That's achievable. That's within reach of current science. Whether it happens depends on research, funding, regulatory approval, and 1,000 other factors that have nothing to do with biology. But the dinosaur connection matters because it shows us something we often forget. We are not the endpoint of evolution. We're a waypoint, a specific solution to a specific set of historical circumstances. Those circumstances shaped us profoundly, in ways we're only beginning to understand, and they constrain what we can become, even with technology. The dinosaurs ruled for 165 million years and then vanished in an afternoon. Mammals inherited their world and built something entirely different. Not better, not worse, just different. And now we're at another inflection point, trying to transcend the biology we inherited, using tools our ancestors couldn't have imagined. Whether we succeed or hit a wall, whether we add decades to human life or discover we've already reached our limit, the story remains the same. We're shaped by deep time, constrained by ancient crises, carrying forward the accumulated weight of every generation that survived just long enough to pass something forward. Understanding that doesn't free you from it, but it does explain why certain paths are open and others are closed, why some changes come easily and others never come at all. That's the legacy of the age of dinosaurs. Not fossils in museums or movies about theme parks. A fundamental reshaping of mammalian biology that still constrains us 65 million years later. We're trying to escape it, compensate for it, work around it. But we can't pretend it doesn't exist. The bottleneck is real. And we're still living on the other side of it, trying to reclaim what was lost when our ancestors had to choose between longevity and survival. And survival was the only option that mattered.